Goolsby. It's changed slightly. Go ahead.
Okay. So you have weight 1 and negative weight 1 plus tension, and then minus tension minus the force of static friction plus weight 2 in the parallel direction.
Weight 1, which is negative. The two tensions you can see are going to cancel one another out. And then the force of kinetic friction is in the opposite direction from positive, and weight 2 in the parallel. Great. So the two tensions are going to cancel out. What is this equal to? So
mass and acceleration.
True. What are we missing? Justin.
In the parallel direction, acceleration.
The acceleration in the parallel direction. What else? Heather.
It's mass 1 plus 2.
So I'll put the total mass for now. But you need to be careful because we're summing on the whole thing. Then that mass that we're talking about is going to be the total mass. Carol.
Weight 1 didn't in the parallel direction.
Ah, it is. Because what the string does is it changes the direction. Okay? So the string, you just follow the string along, and this whole thing is the parallel direction. Okay, so we've got then, let's substitute some stuff in equation-wise. Kenzie.
We know that the weight of the weight of object 1 is just mass times g. So mass 1 times g. And then we
Please
know
don't say G, please say
the acceleration.
due to gravity. You can say on here on Earth if you'd like, but we could do this on any planet. Like, it doesn't matter.
Then we
Keep going.
have, negative.
Ooh, who said static friction? That's not right.
Kinetic.
It's kinetic friction. Minus.
Negative UK times force normal plus mass times acceleration due to gravity times sin equals just mass times acceleration.
I'll put mass 1 plus mass 2 times the acceleration in the parallel direction. Missing one subtle thing, Kevin?
Subscript on actually sign.
The mass for the second one for mass times 2 times the g times the sine of theta. Okay, let's see. What's the problem here?
We don't have force normal.
Okay, so we're stuck. If you look, we actually know everything with the exception of the acceleration in the parallel direction and the force normal. The acceleration in the parallel direction is what we're trying to find. Therefore, the force normal we need to find. How are we going to find the force normal, Emily X? Sum of the forces in what direction? Perpendicular direction. What else? We're not done identifying everything yet. What else, Justin?
Just mass 1.
On just, well,
Mass
actually, I think mass 2. So just on mass 2. Sum of the forces in the perpendicular direction on mass 2, please, Evan.
Force normal minus W or weight 2 perpendicular. That equals mass 2 times acceleration. Parallel or perpendicular.
Okay, good. Work with that, Mario, please.
Acceleration perpendicular is 0.
You know this because
It's not moving weight.
it's not moving perpendicular to the surface, it's only moving parallel. Good. So we get that the force normal is equal to the weight 2 in the perpendicular direction. Weight 2 in the perpendicular direction is going to be mass 2 times the acceleration due to gravity times the cosine of theta. What now, Shilpi?
Substitute mass 2.
now have the force normal. We can substitute that back into the equation. We get negative mass 1 times the acceleration of gravity minus the mu k times the force normal, which is mass 2 times the g times the cosine of theta, plus mass 2 times, mass 2 times g times sine of theta equals mass 1 plus mass 2 times the acceleration in the parallel direction. Our goal is to solve for the acceleration in the parallel direction. We'll put that up here. The acceleration in the parallel direction then is equal to negative m1 times g minus mu k times mass 2 times the cosine of g times the cosine of theta plus mass 2 times g times the sine of theta, all of that divided by mass 1 plus mass 2, the acceleration in the parallel direction. Please help me here. I need all the numbers. Rebecca, please give me all the numbers. Negative mass 1.
2,
G,
9.8,
positive or negative?
positive,
Good.
minus,
Coefficient of kinetic friction?
0.1,
Mass 2.
6,
G, 9.8, cosine of
55,
55 degrees, plus mass 2, which you said was 6 times the acceleration of gravity, 9.8 times the sine of 55 degrees. All of that divided by mass 1, which was, you said was 2, plus mass 2, which was 6, the acceleration in the parallel direction.
3.149.
3.149 meters.
19.
Say again?
3.149. Whatever.
I don't know what the whatever means, but that's what we got. 3.14.
I got 2.96.
Uh-oh.
Yeah.
Or 2.96. Always fun when we have an or on the board. Bless you. Let's start voting. When you have something, let me know.
One second, I got 3.49.
Can you give me something after the 9? 9.1. Okay. So with sig figs, 3.15 meters per second squared. So right now we know whether we picked the correct direction or not for the direction of the force of kinetic friction. Who could tell me how we know whether we picked the correct direction? Planning.
It's positive.
What's positive?
The acceleration.
The acceleration is positive, therefore
It's going that way.
the direction we said it was going to be going. Okay. What if we had picked the wrong direction? What would we get then, Flanagan?
A negative.
We'd get a negative acceleration, and what would we have to do then?
Change the direction.
We'd have to go back and change the direction of the force of kinetic friction. We would have to come back to right. We'd have to fix our free body diagram and change that right there. Okay, so we have the acceleration in the parallel direction. That's part A. Part B, the tension in the string. How are we going to solve for the tension in the string? Look.
Yes. We are going to sum the forces in the parallel direction of mass 1.
And notice, you've got, give me the direction and the object. Keep going.
Equals tension minus weight 1.
Coming over here, bless you, we have tension and weight 1. Keep going low.
Equals mass 1 times the acceleration in the parallel direction.
Good. Keep going, please. Jessica.
oh, where?
We're solving for tension. This is where low has us.
Do you want me to sum forces?
We're actually still working with this equation.
I'm sorry, I was.
Okay, let's back up. Remind me, what are we trying to find at this point? Lynn.
Tension.
So we have this equation, Jessica. We're solving for tension.
Oh, okay. T equals
T.
tension. Equals net, mass times acceleration,
mass 1 times acceleration in the parallel direction plus weight.
Okay. Landon?
You can say that weight 1 equals mass 1 times acceleration. I mean acceleration in the parallel direction. Gravity, sorry.
The acceleration due to gravity, which is the little g. So we have all of these numbers now. Tension equals mass 1 times the acceleration parallel plus the acceleration due to gravity. Mass 1 was the 2. The acceleration due to gravity is our 9.8 and 3.1491 plus 9.8. Tension equals, please.
25.8982.
25.8982 with sig figs, 25.9. Okay, let's review some things. Actually, let's back up. We'll approach this slightly differently. Originally, Connie had us summing the forces in the parallel direction on mass 2. Okay. Do you see how what that would have done? It would have left us with tension and force normal and acceleration all as unknowns, right? But that would have been helpful when trying to find the tension because we would have figured out the force normal and the acceleration. We could have just used that equation. So we could have, at this point, in order to figure out tension, we could have sorted the forces on mass 1 in the parallel direction. We also could have summed the forces on mass 2 in the parallel direction. Either way, we're going to get the same thing. So let's review. When drawing our free body diagram, the steps. Class, first we draw the free body diagram, then break forces into components, then redraw the free body diagram. After that, sum the forces, then we're to the point where now we can sum the forces not just in both directions, but on one object, or on another object, or on all the objects in 2 different directions on those objects. Do you see how many different times we can sum the forces? Then we'll start adding torques. It'll be fun. Okay. Now, some differences between what we did this year and what we did last year. We've added some pieces to make sure that we can, I want to make sure we identify what those are. Maria, give you something new we did this year in this problem that we need to make sure we remember. We have 2 objects. What does that mean? I agree with that, but what does that mean in terms of solving the problem?
We have to you have to use the total mass.
You have to use the total mass at times, true. But it also has to do with an issue I run into with students when they're solving the problem. You guys historically have a hard time helping me understanding what you're doing. What am I talking about here, Flanagan?
You have to specify.
You have to specify. A lot of times you guys want to sum the forces in the parallel direction and you just assume, well, he knows I'm just talking about mass 2. No, you need to specify mass 1, mass 2, or total. One other thing you have to identify, Ciccarelli. It's okay. One other, I'm sorry, go ahead.
Positive.
The positive direction. Whenever you have a pulley, you have to identify the positive direction. Now, truth is, we didn't have to guess. We could have figured out which direction it was going to go when looking at this equation. You could tell me how we would know when looking at this equation which direction it was going to go. We would have to plug in numbers to figure it out, but we could, right here, figure out which direction. Ms. Martins?
Is it because mass 2 is greater than mass 1?
Not necessarily. That's why I'm asking the question, because it's not necessarily just because mass 2 is greater than mass 1. Sure.
Do you have to compare like mass 1 times gravity and mass 2 gravity side?
They're comparing these 2 values here, right? It comes down to comparing those 2 values and which one's greater to determine which way it's going to go. Ladies and gentlemen, people, thank you very much for learning with me today. I enjoyed learning with you. I look forward to seeing you next time. I'm going to do it later.